image points here are actually the same point, right? So f of A would be equal to f of C, right? And from that you prove that A equals C. So you prove that this point is equal to that point. And it has to be that way if it's injective, okay? And if these 2 points are different, then it's not injective. So this technique here, you start with, you take any two, assume they're equal, and then from this prove that A equals C, that they're the same point in your domain. All right. How do you prove surjection? Well, surjection. So we're here. Take any point in your codomain, in your target set, and you know your f. So for any element belonging to B, to your target set, your codomain, if you can find a member of A that maps to that member in B, and that's true for no matter what member this is. If you can find a little a, if you like, that maps to that point, or one or more, but at least one, okay? If you can do that, then it's surjective. So putting that a little more formally, so how to prove a surjection, or that your f, your function, is surjective? How do you do that? You just for each member of your B, so here we've only got two, so you do two tests. So for each member of your target set, your codomain, you're getting used to this terminology already? Okay. So for each one, you find a member of A that maps to this, right? One or more. And if you can do that for each member of your codomain, then it's surjective, because that's the definition, right? Surjective means that every element of your B gets mapped to. You don't have these stragglers, these unconnected, unmapped, right? In a surjection, all members of your B are mapped to you. Alright? So here's a more formal definition. So for each member, find a member of little a from your domain. So just find an A such that that little a gets mapped from into your little b. So in practice, for this diagram, you look at this one and you find little a here. You look at this one and you actually find two. You find two members of A that map to it. So both are mapped to. Okay, so this very simple function, very small sets, starting set, target set, domain, codomain. So they're both mapped to, therefore it's a surjection. Now a bijection is just both. Now if you're asked to prove that a candidate function is a bijection, you have to, it's sort of like an if and only, it's a two-part problem. So to prove something is bijective, a function is bijective, you have to prove that it's injective and surjective. Okay? Because a bijection is both injective and surjective. A bijection is an injection and a surjection. Okay? Alright, so that's proving that something is a surjection. Now, how about disproving it? Like, if you make an analogy, how do you prove something is a group? Well, you have to go through all those four properties, remember, earlier lectures? And how do you prove that something is not a group? Well, you just take just one part of one of those four criteria, and if it fails, then the whole, it's not a group. So disproving something, a function, is a surjection. You only need to, like here, let me give you an example. Take this function, right, with its three parts, right? The domain, the codomain, and the rule, the function. tells you how to map members of your domain onto whatever of your codomain. Okay. Now look. Let's say we're asking the question: is this F? What do we say? Surjective. Is it onto? Is it an onto? ONTO, onto function. Well, immediately, just by looking at it, you can see that it's not. It's not surjective. It's not an onto function. Why? Because here you've got a straggler. Right? Here's an element here that is not connected to. It's not mapped to by anything. Right? It's a straggler. It's on its own. It's a little stranger. Right? So therefore, this function f here is not surjective. It is not an onto function. Okay. So to find to prove that a candidate function is not surjective, is not onto, all you have to do is just find one element that's not mapped to. Okay, so it's a pretty simple concept. So here, oh, I haven't. Yeah, so find an element of your codomain here. Find an element here, like this one, so that that there's no mapping. So for all your FAs, all your images of A's, you're mapping all. You have to, right? Because it's a function. You have to map all members of your domain. If you don't do that, it's not a function. It's not defined. Right? That's strict. So all of your images of all these, all your F of A's, little A's, for every member, if none of them equal, we'll call that little b here, if none of them, if all the images of these points, call it an image set, like, well, I didn't talk about that, perhaps I should right now. So all these three map to these two, okay? So this is the image of that one, and this one is the image of that one. Now this set of all the images is called, surprisingly, an image set. Okay, it's the set of the images. An alternative name for an image set is just the range. Okay? So the range could be a subset of your codomain. And now here it is, like this. I don't know if you can see the stippled little oval here. So these two, that's a subset of your codomain because this element here is not mapped to. Okay, it's a straggler, if you like. So if your range is not the same thing as your codomain, in other words, there are elements that do not belong to your image set, then this function here is not surjective. It's not an onto function, right? So basically, you can just look at the function if it's done visually, like in Venn diagrams, for example, and you just go looking for the strays, the detached, the unmapped members, and if you can find just one's enough. So if you can find just one, you don't need to bother finding others. One's enough. So if you do find one, then that F is not surjective. It is not an onto function. Okay? So that's your strategy when you're trying to disprove a surjection. To prove that your candidate function f is not a surjection, is not surjective as an adjective. You just go looking for some member of your codomain that is not mapped to from your domain. Okay. Right. Okay. So if you want to prove a function is bijective, you have to prove that it's injective, and to do that you do this, okay? And you have to prove that it's also surjective, and to do that you do this. Now if you suspect that it's not surjective, use this approach, and then if it's not surjective, it's not bijective. Okay? Because bijection means it has to be this and that. So if one or two of these two is not satisfied, not true, then it's not bijective. It's not a bijection. Okay. Now, normally I do the problem-solving part at the end, but this time I think I'll make an exception, because there are a couple of theorems still remaining in the theory part, but they make so much more sense after you've got a fairly solid dose experience of solving problems of this type, that I think it probably makes more sense to do the problem-solving part now, and then I think I'll go back and then give you a couple of theorems left in the theory. So I'm putting the problem-solving part now in the middle. Be back.